A very good morning to one and all. Dear students, hope all of you are safe at home due to this widespreading COVID-19 disease. And as per the orders from government and from government authorities, I request all the students to follow these instructions. Also at the same time, it is very important to follow the instructions of professional bodies of engineering courses in context of this widespreading COVID-19. The APJ Abdul Kalam Technological University and All India Council for Technical Education stressed the importance of rely upon the online resources to learn the engineering subjects. So it's very important to see that at least for this semester the students are supposed to rely upon the online resources. According to me, there is rare chance or there is no chance to extend the semester or the university examination. So all this will going to affect the course or examination process. So you may please note that more than 50% of the students, both in engineering and also in arts and sciences, started depending upon the online resources and started learning the courses. And if you are a step behind and not started yet, you are going to lose the rhythm and it may affect in clearing the subjects of this semester. So many people, institutions are well ahead of us. You may please know this. So utilize the time depending on online resources shared by the faculty. Follow it correctly. It's highly needed. So again, as per the direction of APJ Abdul Kalam Technological University, we faculties are also instructed to rely on the video lectures, online resources, etc. during the study period. So please note that we also will carry out the continuous evaluation in terms of internal assessment, assignments to the available online resources to substitute what we generally give in the classroom as classroom instructions planned during the semester. So I wish all students to have a safe and nice time at home. Be safe, don't go outside, control yourself to get away from this COVID-19. And so we have learned about the refrigeration and air conditioning. We started learning about the air conditioning and refrigeration. And I have shared you many resources like the video, animations, etc. to understand the subject. So this would be the first video lecture recorded by me for you. So we learned about what do you mean by refrigeration and what do you understand by a refrigerating system and what do you mean by a refrigerant, what do you mean by a refrigerator, what are the applications of refrigeration, and we also defined the refrigerating capacity, the unit of refrigerating capacity, and we also defined the coefficient of performance. We also have discussed about the reversed Carnot cycle. Continue to this. Today we are going to learn about one of the important cycle related to a refrigerating system. So this is one of the commonly used cycle used in a refrigerating system, which is called the vapor compression cycle. Let's start with the lecture directly. Yeah. So in a vapor compression system or in a vapor compression refrigerator, the working fluid is a vapor. It has a characteristic. What is it? Its characteristic is which can readily evaporate and condenses. Which means during the evaporation, there are two processes which we will learn while learning the subject. So during the evaporation, it absorbs heat and get converted from liquid to vapor, and during condensation process, it rejects heat and get converted from vapor to liquid. Now, in a simple vapor compression system, it consists of following components: a compressor, a condenser, expansion valve, and an evaporator. So what you can see in this slide is a schematic diagram which shows a simple vapor compression system. So it's a line diagram which represents a simple vapor compression system. Now you can see that I have marked the compressor, the condenser, expansion valve, evaporator, etc. And you can also see the points 1, 2, 3, 4 which are marked in this diagram. And let's see what does it all represents. Let's start discussing about the working of this vapor compression system. Now let's start from this point 1, which means something which is coming out from the evaporator. Let's put it as the starting point. Yes, this one. So assume, let the vapor leaving the evaporator be dry saturated. What do you mean by a dry saturated vapor? It means all particles in the vapor or all the particles are vaporized. So this dry saturated vapor, let's assume that the conditions of this dry saturated vapor, which means the pressure P1 and temperature T1. So this dry saturated vapor at pressure P1 and temperature T1 is drawn into the compressor cylinder during its suction stroke. You can see that this is a compressor. You can see that this is a cylinder piston arrangement. The piston can move in and out. So the dry saturated vapor at pressure P1 and temperature T1 is drawn into the compressor cylinder during its suction stroke, and during the compression stroke the vapor is compressed isentropically to pressure P2 and temperature T2. Now you know that what do you mean by an isentropic process, which means a reversible adiabatic process is an isentropic process. We have discussed such all the stuff during while you are learning about the IC engine cycles. So this process is shown by the line 1, which is this is actually this point 1 to point 2 shows this process, which means the dry saturated vapor which is enters into the compressor cylinder during its compression during its suction stroke, and it is compressed to very high temperature and pressure during its compression stroke. Now at the end of the compression, the vapor is in a superheated state, which means very high temperature and very high pressure. So the vapor at this condition now passes to the condenser. If you look at this condenser, you can see that the cooling water is circulated in this condenser. So why the cooling water is circulated? To remove the heat from the vapor. So the vapor is first cooled to saturation temperature, which means from the superheated state it comes to the saturation temperature, where the vapor has the temperature of dry saturated air, and then again further removal of latent heat of condensation, which means further removal of latent heat of condensation means only the phase change occurs from vapor to liquid, no temperature change occurs. So the vapor at this condition, that is a superheated state, it passes through the condenser in which the cooling water is circulated, so to remove the heat from the vapor. So the vapor is first cooled to the saturation temperature, and further removal of latent heat of condensation, it condenses to liquid till the point 3 is reached. Now the high pressure liquid, it goes to an expansion valve, or it is expanded in an expansion valve. It's a throttle valve. The pressure of the liquid coming out of this expansion valve, or the pressure of the liquid, is lowered to, you can see that a pressure called P1, and the condition obtained after constant enthalpy expansion process is shown by the point 4. You can see that this process is a constant enthalpy process. While you are seeing this one, like means where the dry saturated air is compressed into superheated state, that process was an isentropic process, where this process, please note that it's a constant enthalpy process. And during throttling, the liquid partly evaporates, and after throttling, we get wet vapor at low temperature T1 and low pressure P1. So this wet vapor passes through, you can see that the evaporator coils immersed in the brine solution. So this, what actually happening here is a wet refrigerant vapor absorbs the latent heat of vaporization from the brine solution and evaporates. So after evaporation, the vapor reaches the condition given by the point 1, that is the dry saturated at pressure P1, which means it reaches this point again. So this complete one cycle of operation. So I will repeat once again for your understanding. You have a dry saturated vapor now. It passes through the compressor. The dry saturated air is taken during the suction stroke and is compressed due to very high temperature and pressure, that is superheated state. At point 2, it passes through the condenser, where the cooling water is circulated through the condenser, and when it passes through the condenser, it first lowered to saturation temperature, and again removing the latent heat of condensation, it becomes a high pressure liquid. Point 3, now it passes through the throttle valve or expansion valve, constant enthalpy process. It reaches to point 4, and again it passes through this wet vapor coming out of the expansion valve. It passes through the evaporator, and please note that the cold brine solution is circulated in coils around the space to be refrigerated. For example, imagine the case of the cabin inside the refrigerator. So that is a place where we need refrigeration effect is needed, isn't it? So usually this cold brine is circulated in coils around the space to be refrigerated. And what actually happens is, inside the refrigerator cabin, again these evaporator coils are also immersed in a brine solution. So this cold brine solution, which absorbs heat from the food and foodstuff, and it ensures a cooling effect inside the refrigerator cabin. Now actually what is happening, the place where the evaporator coils are immersed, that brine solution actually absorbs heat from these food products, and while the wet vapor which is passed through the evaporator coils takes this heat from the brine solution and convert it from wet vapor to dry vapor. Now here in this vapor compression system, let's see what is a net refrigerating effect. The net refrigerating effect of this system is the heat absorbed by the refrigerant from the brine solution. How much heat it can absorb from the from the brine solution, where the evaporating coils are immersed into. How much heat it can absorb from the refrigerant. So it depends upon the wet vapor, isn't it, which passes through the evaporator. Now the work done by the compressor is the work spent to produce this refrigerating effect. Please note that the work done by how much work the compressor can do. The work done by the compressor is the work spent to produce this refrigerating effect. Therefore, The coefficient of performance of a simple vapor compression system is equal to the heat extracted in the brine solution divided by work done by the compression. How much heat can extract from the brine solution by the wet vapor divided by work done by the compressor. So that is the coefficient of performance. Thank you. Here we are coming to the end of this lecture. On next class we will come with another topic. Thank you.